In this lesson, we are going to discuss lens equation. At the end of this video lesson, you should be able to predict the qualitative characteristics of images formed by lenses using the analytical method or the lens equation. Just like in mirrors, ray diagramming in lenses does not give us exact measurements of the distance and heights of the objects and images. Ray diagramming only allows us to qualitatively describe the images formed. But just like in mirrors, we can also quantitatively describe the images in lenses using the analytical method. We are going to use the lens equation to relate the object distance, image distance, and the focal length of the lens. This is the same with the mirror equation. The lens equation will tell us the type and orientation of the image that will be formed. To describe the size of the image, we are going to use the magnification formula. It is the ratio of the height of the image to the object. It is written as magnification, or M, is equal to the ratio of the image height and the object height, which is also equal to the negative ratio of the image distance and the object distance. And just like in mirrors, we are going to compare the magnification of the image to 1 to describe the size of the image. If the absolute value of the magnification is equal to 1, the image is the size the same with that of the object. This is also the case if the object height is equal to the image height. If the absolute value of the magnification is greater than 1, the image is larger than the object. This is also the case if the object height is less than the image height. Lastly, if the absolute value of the magnification is less than 1, the image is smaller than the object. This is also the case if the object height is greater than the image height. Aside from these rules, we also need to be careful and knowledgeable with the sign conventions. In lenses, only the focal point has a different sign convention compared to mirrors. A positive focal point is concave in mirrors but convex in lenses. A negative focal point is convex in mirrors but concave in lenses. The rest of the components will be the same with mirrors. A positive image distance means that it is real, inverted, and formed on the other side of the lens. A negative image distance means that it is virtual, upright, and formed on the same side of the lens. Now, let us solve some word problems on lenses. For the first problem, an object is placed 12 cm from a convex lens and an image appears at 24 cm on the opposite side of the lens. What is the focal length of the lens? How many times is the image magnified? And do a ray diagram for this image formation. Let us first identify the given. The object is placed at 12 cm in front of the convex lens. This is our D sub O. Next, it has formed an image which appears at 24 cm on the other side of the convex lens. Thus, its image distance is 24 cm. Take note that the image is positive because it is real. Real images are found on the opposite side of the lens. We are going to solve for the focal length of the lens. To solve for this, we are going to use the lens equation, which is 1 over d sub O plus 1 over d sub I is equal to 1 over f. Plugging in the values, we are going to have 1 over 12 centimeters plus 1 over 24 centimeters is equal to 1 over f. Just like in mirrors, the answer of this expression is not yet the final answer. Thus, we're also going to do the reciprocal. We can do this using two ways, maybe depending on your calculators or how you're going to solve this problem. First, we could just stick with the fraction format. 1 over 12 plus 1 over 22 is equal to 1 over 8 centimeters. Take note that this is equal to the reciprocal of f. This is when we are going to do the reciprocal of both sides. Thus, we have 8 is equal to f. This is our focal length. But let us check if this would also be the answer if we answer it using decimals. 1 over 12 and 1 over 24 would add up to 0.125 centimeters. And again, this is still 1 over f. To solve for f, we get the reciprocal of both sides. This gives us 1 over 0.125 centimeters is equal to f. Both fraction and decimal solutions would result to a focal length of 8 centimeters. Although not asked, we can identify that this lens is a convex lens because the focal length has a positive sign. Let us now do the second unknown. Here we are going to solve for how many times the image is magnified. This means that the magnification or m is unknown. Thus, we are going to use the magnification equation in terms of the negative distance ratio. We use this equation because we do not have a value for the object and image heights. We only have the object and image distances. To solve for this, let us plug in the values. M equals to negative d sub I over d sub O is equal to negative 24 centimeters over 12 centimeters. We are going to cancel the unit for height, which is centimeters. Thus, negative 24 divided by 12 is negative 2. The negative sign of the magnification value here does not tell us that the image diminished in size. Rather, it tells us that it is inverted. The absolute value of the magnification value tells us the size of the image. Since it is greater than 1, it is enlarged. Let us check our solution by answering the last item for this problem. We are going to draw a ray diagram for this image formation. Here we have our convex lens ray diagram. We cannot yet put the object since we need to plot first the value for the focus. On our computation, the focal lengths on both sides are equal to positive 8 centimeters. This means that the centers of curvature are 16 centimeters because the center of curvature is twice the value of the focal length. Now, we can put the object. Since the object distance is 12 centimeters, it will be placed in between 8 centimeters and 16 centimeters. That means our object distance is less than 2f sub 1 but greater than f sub 1. From this, we can now do our ray diagram. For the incident principal ray, we have a ray going to the lens but in the direction parallel to the principal axis. It will refract away from the lens going to f sub 2. For the incident focal ray, we have a ray from the top of the object going to f sub 1 until it reaches the lens. It will refract away to the lens parallel to the principal axis. Lastly, we have the central ray that will pass continuously from the top of the object to the optical center and away from the lens. The point of intersection is the position of the image. As we can see here, the image is real, inverted, and enlarged. This agrees to our computed image distance of 24 centimeters and a magnification of negative 2. Now, let us look at the last problem. A 5 cm high object was placed 4 centimeters in front of a lens to form an image with a height of 3.19 centimeters. What is the focal length of the lens? Let us first identify the given. The phrase a 5 cm high gives us the object height. This means that this is our h sub O. Next, it was placed 4 centimeters in front of the lens. That means this is the object distance. We have d sub O is equal to 4 centimeters. Lastly, it created an image with a height of 3.19 centimeters. This gives us the image height. Take note that since it is not specified if it is formed on the same side or the other side of the lens, or if it is upright or inverted, we are going to stick with the positive value for the image height. We are asked to solve for the focal length. Thus, we are going to use the lens equation 1 over d sub O plus 1 over d sub I is equal to 1 over f. However, looking at our given quantities, we do not have an image distance. This is the only equation that could give us the focal length. That's why we need to think of a way to compute for d sub I. Remember that the image distance can be computed using the magnification equation. In this case, it can be computed using the magnification equation involving the height ratio being equal to the distance ratio. To solve for d sub I, we are going to multiply both sides of the equation by negative d sub O. Thus, we have the image distance is equal to the image height times the negative of the object distance all over the object height. Plugging in the values, this will become 3.19 centimeters times -4 centimeters all over 5 centimeters. Before we compute for the answer, we are going to cancel 1 unit in the numerator and the unit in the denominator. This would give us -2.552 centimeters. With this, we can now solve for the focal length of the lens. We are going to plug in the given quantities to the lens equation. Thus, we have 1 over f is equal to 1 over 4 centimeters plus 1 over -2.552 centimeters. 1 over 4 centimeters plus 1 over -2.552 centimeters is equal to -181 over 1,276 centimeters when using fractions in the solution. Take note that this is equal to the reciprocal of f. This is when we're going to do the reciprocal of both sides. Thus, we have -1,276 divided by 181 centimeters is equal to f. But let us check the solution using decimals. 1 over 4 centimeters and 1 over -2.552 centimeters would add up to -0.1418 centimeters. And again, this is still 1 over f. To solve for f, we get the reciprocal of both sides. This gives us -1 over 0.1418 centimeters is equal to f. Both solutions should give us a focal length which is equal to -7.05 centimeters. This agrees with our computed image distance, which is a negative value. A focal length of negative value means that a concave lens is used. Concave lenses creates virtual images as evidenced by the negative image distance. Aside from this, the image is reduced. Concave lenses form virtual, upright, and reduced images. To summarize this lesson, let us review the following key points. The lens equation is an analytical method to predict the qualitative characteristics of images formed by lenses. The lens equation relates the object distance, image distance, and the focal length of the lens. And lastly, the magnification is the ratio of the size of the image to the size of the object. And that ends our discussion on the lens equation.